All right, we're going to take a look at problem 12 on the second semester review. So I think we're actually on page 4.6 overall, number 12, a rational function, which we know has to be factored immediately. We are going to factor the top as the sum of cubes. So you really want to know that sum of cubes formula. A plus b times a squared minus ab plus b squared. So the cube roots of 8 and x cubed are 2 and x. And then 2 squared is 4, x squared is x squared. Those are your first and last terms. In the middle term would be the 2 times the x. Now notice, because this is plus, that middle term will be the opposite of that, minus. And that's your cube, your sum of cubes kind of formula. The bottom is going to factor twice because we can first take out an x, factor out the common term, but what's left is difference of squares, so it's kind of a composite factorization there. We notice three, I guess what we would call bad numbers. Bad zeros that make zeros in the denominator, 0, positive 2, and negative 2. Any of those numbers would create a 0 in our denominator, which would create an undefined value, either from a vertical asymptote or whole. It really doesn't matter what it is. They create undefined values. They have to come out of the domain. You don't get a, worry about that. Some people might ask, well, didn't we learn how to fix those in an extended function? Well, yes, we did, using using limits, but that's not what we're doing in this problem. We're defining the domain of the original function. And so take those numbers out. Every other number is good. So I only took 3 bad numbers out. Every other number was okay. Now we have to analyze those numbers. And 2 of them did not cancel, right? These 2 right here did not cancel with any factors above. So 0 and 2 become vertical asymptotes. Meanwhile, the last one did cancel. Those guys right there, 2 plus x, x plus 2 mean the same thing. So negative 2 is a whole. Okay, now notice we did the domain, vertical asymptotes, and half the wholes just by factoring and looking to see what canceled. That's half the problem. So factoring is huge, huge, huge. Now, how do we figure out the second part of the whole? Well, we're going to have to do some algebra. We're going to have to take those x plus 2's out so that we don't get the zeros in the top and bottom anymore, and see what happens with the rest of the function when I do plug in that negative 2. Let's see what happens. It looks like we plug the negative 2 on the top, a negative squared is positive, negative times negative is positive, so I get a bunch of positive 4's on top, and a negative 2 times a negative 4, which will create a positive 8 on the bottom. So 3 halves, it looks like. 3 halves is the y value of our whole. The possibility of horizontal asymptotes comes from examining the end behavior. And it looks like the end behavior is going to be converging, so there will be a horizontal asymptote. Notice the power of the top, the degree of the top is 3, the degree of the bottom is 3, so our end behavior model is just x cubed over x cubed, which we know is 1. So we should end up with a horizontal asymptote at 1, and that's how easy horizontal asymptotes are. They only occur if the powers are even, and then you look at the coefficients, or if the degree of the bottom, the power on the bottom, is greater than top, and then of course we collapse to 0. Notice these problems weren't giving you like end behavior shifts. If they were, you'd have to factor that in to your calculations, but at least on 11 and 12 here, that did not happen. So we're 80% done with this problem. The only thing we have not come up with yet is the range. And that's, of course, because you can't come up with the range until you graph it. So here is our graph. Notice the horizontal asymptote that we found at 1, and I graphed that for you. You can see that is part of the graph. And it looks like this graph has what I call a jump gap. So between the horizontal asymptote up on the top and the top of that, I guess we call that a local max at the point 1, negative 3. I used a calculator to find that. I did an analyze maximum value. I have no y values though. I have no y values that are hit. This entire little sequence right here of y values never gets hit by my function. So those can't be part of the range. So what is the range then? Well, the range is all values coming up from negative infinity until I get to this height at negative 3. I will include that value though. That vertex does get hit by the graph, and so I'm going to go ahead and include that. And then I'm not going to start my y values again, my range values, until I get on the other side of that of that asymptote. Now, we saw an example yesterday, I think it was problem 8, where on one of the sides we crossed down through the horizontal asymptote and then approached it from below. And so we had to kind of find this local minimum value here to know where the range started again. And I did not need to take the horizontal asymptote out because it got hit by the graph. Horizontal asymptotes, unlike vertical asymptotes, can in certain conditions be crossed. But in this case, we do not see that. This graph is approaching the horizontal asymptote at 1 from above in both cases. So we never hit 1. So that means I will start just above 1. So I would use a parenthesis to describe that. And then we would go up from there, wouldn't we? We would go straight up, and this graph is going to go up towards infinity. I guess the last thing we would ask is, we found a hole, didn't we? Didn't we find a hole at, where was it? It was at -2, and then 1.5, I think. So I think it was right around here. Normally we would have to take that y value out, but if you go over to the other side of the graph, it looks like we're going to hit that same y value here. And so that means the hole is covered. That's how we phrase that. And so that value does not need to come out of the range. So our range is going to go from -infinity to 3, -3, I should say. Notice how we are including that value with the bracket. And then we start again at 1, but not including 1, hence the parenthesis there, and then on up to infinity. So there's the range, and that finishes off problem number 12, a rational function. Always a lot of fun.